Greetings, the internet. This video will be on infinite series and sequences. Before we begin this video, I just want to give a special thank you to whoever the one person liking my video is. Thank you. The importance of infinite series and sequences in calculus stems from Newton's idea of representing functions as sums of infinite series. For instance, in finding areas, he would often integrate a function by first expressing it as a series and then integrating each term in the series. Many of the functions that arise in mathematical physics and chemistry, such as Bessel functions, are defined as sums of series. So it's important for us to be familiar with basic concepts of convergence of infinite sequences and series. Physicists also use series in studying fields like optics, special relativity, and electromagnetism. They analyze phenomena by replacing a function with the first few terms in the series that represents it. What is a sequence and what is a series? Well, a sequence is a list of numbers in an order. So for an example, a sub 1, a sub 2, a sub 3, and so on all the way up to some number. It's a list of numbers in a particular order. So we could do another example. So another example of a sequence could be 1, 1 over 2, 1 over 3, 1 over 4, all the way up to 1 over some number. That's a sequence. Now a series is what you get when you add all of the terms of a sequence together. So as an example of a series, a sub 1 plus a sub 2 plus a sub 3 plus a sub 4 plus everything that's between that and the ending number. Now, just note that we just took a sequence and we just added it together. If I were to create a series from this sequence here, it would look like this. Now, this would be a series that's created from this sequence up here. Now, note that the sequences have brackets. They have these braces, is what they're called, braces or curly brackets, whatever you'd like. Those are usually found with sequences. So in short, a sequence is an ordered list of numbers, and a series is the sum of the numbers in a sequence. All right, now check this out, because here's an example of a sequence right here. A sub n equals 1 over n. And then the series for this sequence would be as follows. All right, and that's because we're summing all of the terms of the sequence together. Now, as for convergence and divergence, a convergent series is an infinite series that has a finite sum. So if a series converges, it settles to one number, and if it diverges, it does not settle to one number. Let's work through a couple of examples. So here we're asked to evaluate the geometric series or state that it diverges of the summation from k equals 0 to infinity of 1 over 13 raised to the power of k. All right, so here's the constraints. If a is not equal to 0 and r is real numbers, and if the absolute value of r is less than 1, then the infinite series from k equaling 0 to infinity of a times r raised to the power of k, that's going to equal a over 1 minus r. Now, if the absolute value of r is greater than or equal to 1, then the series diverges. So how do we evaluate this geometric series? Well, in order to do this, we need to write out the first few terms of the series. So how do I evaluate this? Well, we're starting at k equals 0. Therefore, I'm going to plug in 0 for k. Now this is summation, so plus what comes after 0? 1. So we're going to plug in 1 for k. Likewise, the next partial sum is going to follow the same pattern. What comes after 1? 2. So we're going to raise 1 over 13 to the power of 2. And the series will continue onwards. We only need the first few terms, because in order to determine if the given series diverges or converges, we need to find r. But to find r, which stands for ratio, by the way, r stands for ratio. To find the ratio, or r, we need to divide any term in the summation by its preceding term. 1 over 13 raised to the power of 1 is going to equal 1 over 13. All right, so then we're going to evaluate 1 over 13 raised to the second power. And this is going to equal 1 over 169. So now what we'll do is 1 over 69 divided by 1 over 13, right? And so this is going to equal 1 over 13, which means that 1 over 13 is the ratio. So we'll set that to r. And you might ask yourself why this is of any importance. Well, we know now that the ratio is 1 over 13, okay? So if you divide 1 by 13, it's going to be less than 1. All right. Now, if the absolute value of the ratio is going to be less than 1, that means that we can apply this formula here, a over 1 minus r. So that begs the question, what's a? How do we find a? What does a even stand for? Well, a is going to be the first term in the series. Let's look at the first term in the series that we started off with in the summation. Well, the partial sum 1 over 13 raised to the power of 0 is going to be the first term in the series, and anything raised to the power of 0 is just 1. Therefore, a is going to be 1. Now we have everything that we need to put on for our formula. So a over 1 minus r, it's the same thing as 1 over 1 minus 1 over 13, our ratio. So this is the exact same thing as 13 over 13 minus 1 over 13. 13 over 13 is a form of 1. What's 13 over 13 equal to? Well, it's equal to 1. Therefore, I can go through with finding the difference of these two terms here. We have a complex fraction here. We don't want a complex fraction. So in order to get rid of the complex fraction, we're going to reciprocate the denominator. We're going to take the reciprocal of 12 over 13 and multiply it back to 1. And that's going to equal 13 over 12. Therefore, the series from k equals 0 to infinity of 1 over 13 raised to the power of k um, is equal to 13 over 12, and the series converges. All right, let's do another one. Okay, so we're asked to evaluate the geometric series or state that it diverges, and the geometric series is as follows. 1 plus 7 over 10 plus 7 squared over 10 squared plus 7 cubed over 10 cubed, and it goes onwards. That's what that ellipsis stands for. We're going to keep going following this trend. Now, the formula, or if you will, the constraints from before are still applicable. Thus, I'm going to leave that right there. So the first thing to do here is to find the ratio r of the series, and this can be done by comparing the successive terms. We're going to take a look at 7 squared over 10 squared, and we're going to divide it by its predecessor, the term in this series that came before it, which is going to be 7 over 10. 7 squared over 10 squared divided by 7 over 10 is going to be 7 over 10. Therefore, the ratio is 7 over 10. Okay, so the absolute value is less than 1. Notice that when k is equal to 0, a times r raised to the power of k equals a. So in other words, the value of a is equal to the first term in the series. And in this case, it's just given to us. So a equals 1. So what we'll do is we'll use this information to find the value of the series, and we're going to plug into that same formula. So notice that k starts at 1 here, and we're going to infinity. And we're just going to put our ratio right on in the parentheses here, and we're going to raise it to the power of k. So we'll go ahead and we'll take into account this formula here. A is equal to 1. Then we're going to do 1 minus our ratio, 7 over 10. Now, 1 is the same thing as 10 over 10. Now we have a common denominator. Upon subtraction, we'll find that we will have the denominator as 3 over 10, which is a complex fraction, and will reciprocate. So we will do 1 over 1 times 10 over 3, and that's going to give us 10 over 3. So that means that not only does our series converge, but it evaluates to 10 over 3. Now this here says to evaluate the geometric series or state that it diverges for 1 plus Euler's number over 5 pi plus Euler's number raised to the second power over 25 times pi raised to the second power plus Euler's number raised to the third power over 125 times pi raised to the third power, and so on. First thing to note is that I've left our rules here because they're still relevant. But what we need to do is find the ratio of the series as before. So we'll compare successive terms. So to find the ratio, we're going to take Euler's number raised to the second power over 25 times pi raised to the second power. We're going to divide that by Euler's number over 5 times pi. We can reciprocate the second term here. We have Euler's number raised to the second power over 25 times pi raised to the second power times 5 times pi over. So now we have Euler's number raised to the second power over 25 times pi raised to the second power times 5 times pi over Euler's number. There's going to be some cancellation. Pi and pi will cancel. Euler's number and Euler's number will also cancel. So then what does this yield? Well, we're going to have a 5 in the numerator because that 5 is left alone for now. Now, as for Euler's number, you see how it's raised to the second degree? Well, we only were able to cancel out 1, thus there's going to be Euler's number in the numerator as well. So 5 times Euler's number in the numerator. In the denominator, that 25 can be left alone for now. So we're going to have a 25 down here. And then that pi was raised to the second degree. Therefore, we're still going to have a pi in the denominator. Now, both these terms in the numerator and the denominator, 5 and 25, are both divisible by 5. Therefore, I can simplify this to 1 over 5, which is actually going to be 1 e 5 pi, which can be simplified further to just e over 5 pi. What's Euler's number divided by 5 pi? The answer to that is 0.1730511,959. And this can approximate to 0.173. That's what we get when we round it to 3 decimal places. Now that's R, right? 0.173 is set to R. Remember that A is always going to be the first term in the series, and that's given to us as 1. So we'll use this information to find the value of the series. To find the value of the series, we're going to use the formula A over 1 minus R. So K is set to 0, and then up top we have an infinity. Then we're just going to put in our ratio in the parentheses here, E over 5 pi raised to the power of K. That's going to equal what we get when we plug in our terms to the formula here. A is set to 1, and then that's going to be the numerator and the denominator. We're going to have 1 minus E over 5 pi. Okay, well, let's do a form of 1, specifically a form of 1 with a common denominator, so we can take care of the subtraction. 5 pi over 5 pi is the same thing as 1, and we're subtracting Euler's number over 5 pi. Well, that's the same thing as 1 over 5 pi minus E over 5 pi, but this is a complex fraction, and we don't want a complex fraction, so we're going to reciprocate. So this is our answer. That means that the series 1 plus Euler's number over 5 pi plus Euler's number squared over 25 pi squared plus Euler's number cubed over 125 times pi cubed is going to be 5 pi over 5 pi minus Euler's number. Now for this one, we're asked to evaluate the geometric series or state that it diverges for the infinite series from k equaling 2 to infinity of negative 0.65 raised to the power of k. To do this, we have to identify the first term in the given series. Now remember, the first term is going to be a, but when we find the first term, we're not plugging in 0 anymore. We're plugging in 2 because k equals 2. Therefore, that means the first partial sum in the series is going to equal 0.4225. Another way we could write this is S sub n equals 0.4225, which of course also equals a, as we've established. Now we want to find S sub 2, the second term in the series. Well, to do that, we're going to do the same thing as what we did up here, but instead of raising it to the power of 2, we're going to raise it to the power of 3 because 3 comes after 2. Negative 0.65 raised to the power of 3, it's going to be negative 0.274625. And we'll go ahead with an approximation here. Negative 0.2746. Now we have to find the ratio. The ratio is going to equal any term in the series and then dividing that by its predecessor. So in other words, S sub 2 divided by S sub 1. That's going to equal negative 0.65. The series converges since the absolute value, right? We're going to take the absolute value of this. This is the ratio, and we're going to take the absolute value of the ratio. Okay, the absolute value of the ratio is going to be 0.65, which drop in that negative symbol. 0.65, it's less than 1, which means that the series converges. We're going to put on for this formula 0.4225 over 1 plus, right? Because originally when we had the ratio, it was, before we dropped the negative sign, and took the absolute value of it, it was negative 0.65. And we're doing 1 minus negative 0.65, and that's actually going to be 1 plus 0.65. 0.4225 divided by 1.65, well, that's going to be 169 over 660. That's our answer. Let's do another one. But let's do one that's a little bit more interesting. Now I'd like to take a minute to profess my love to the mathematical patterns that reveal themselves in life. I absolutely love thinking about life mathematically and interpreting it through a mathematical lens. This problem says, suppose you take 320 milligrams of an antibiotic every 8 hours. The half-life of the drug is 8 hours, and the half-life means it's the time that it takes for half of the drug to be eliminated from your system, from your blood. And to use the infinite series to find the long-term, steady state, amount of the antibiotic in your blood exactly. This is a very interesting problem. To do this, we need to consider what happens to the initial dose of the 320 milligrams and disregard the subsequent doses. We're not gonna think about that right now. Because after 8 hours, half of the 320 milligrams will already have been eliminated. What amount of drug is going to remain in your blood? 320 times 1/2 milligrams. Now, after 16 hours, this smaller amount, 320 times 1/2, will be reduced by 50%. So if it's reduced by 50%, then what amount of drug will remain in the blood? We got the 320 milligrams multiplied by 1/2. Okay, so let this represent the 8 hours, and then we'll do it again for 16 hours. 320 times 1/2 times 1/2 milligrams. So using that same method, after n hours, we'll say that only 0.5 raised to the power of n times 320 milligrams of the original dose will remain in your system. So to determine the cumulative effect of all of the doses of the drugs, notice that immediately after the time of any new dose, your blood will contain that dose plus the amount that remains of earlier doses. So the question is, what amount of the drug will remain in your blood immediately after the second dose? What's that going to look like mathematically? 320 plus 1/2 times 320, because we're taking into an account the dose that you've taken previously. The blood will contain the nth dose of 320 milligrams plus the amount that remained from earlier dosages. So in order to determine A, which is what we want to find, we're going to compare that series with the general geometric series of this form. All right, let's look for patterns. A, A, R, well, we've already said that 320 is A, and that's revealed to us by the first term, which means that 1/2 has to be R. Okay? R, A, R, A. What does that mean? Well, that means that A is going to be 320 and R is going to be 0.5. But of course, the ratio is also found by dividing any term by the term that directly precedes it. So if we divide the second term by the first term to find the ratio, we're going to end up with R equals 1/2. The infinite series A plus A times R plus A times R squared plus A times R cubed plus A times R to the fourth, and so on, converges if and only if the absolute value of R, right? So it converges if the absolute value of R is less than 1. Now, when the absolute value of R is less than 1, then the sum of the series is going to equal A over 1 minus R. Sound familiar? Well, let's look at the conditions. Well, let's look at the ratio. R equals 0.5. The condition that the absolute value of R is less than 1 is met. Therefore, the sum of the series is going to be A over 1 minus R. So we'll use the formula for the sum of the geometric series with A equaling 320 and R equaling 0.5 to find the values of the sum. And we'll do this by first substituting the values and then evaluating the denominator. I'm going to write the denominator as a fraction. And then I'm going to reciprocate. What was that, 640? 640? 640 milligrams. So that means that the long-term steady state amount of the antibiotic in your blood is going to be 640 milligrams. I love repeating decimals. I'm obsessed with them. I'm obsessed with a lot of things like prime numbers, but repeating decimals, they're just so aesthetically pleasing. I digress. Write the repeating decimal first as a geometric series and then as a fraction, a ratio of two integers. For the repeating decimal, 2.85, such that 2.85 equals 2.858585858585, and so on. In order to evaluate this, we need to separate the repeating part of the number from the non-repeating part. The non-repeating part of the number is before the decimal, it's 2. And then the repeating part is 0.8585858585 and so on. So what we want to do is write out the non-repeating part and then the repeating part as a sum. Okay, so we have 2.85 repeating equaling 2 plus 0.85 plus 0.0085 plus 0.000085, and it goes onward. And it's a geometric series. Specifically, the part that comes after the 2 is a geometric series. So what we need to do is determine the values of the first term, which is a, and the ratio, which is r. Now, to determine the value of a, we're going to look at the first term, which is 0.85. Now we need to find r. We need to look at one of the terms in the series and then divide by the term in the series that comes before that. So we'll take 0.0085 and we'll divide it by 0.85. That's going to equal 0.01. And that's what r will be. Allow me to write out the standard formula for a geometric series. Apiro, la trevonia mathematica. Alright, so here's the standard form of the geometric series, the formula. Now we can write this entire thing as a geometric series, even the part with the 2. What we'll do is we'll put that 2 out front in front of the sigma, and then we'll also put the plus in front of the sigma. So then the summation will be written as follows. We have 2 plus the summation from 0 to infinity of 0.85 times 0.01 raised to the power of k, right? Because we know that a is 0.85, so we put that right here. And we know that the ratio is 0.01, so we put that right here, and we raise it to the power of k to indicate whatever we're plugging in for k as a partial sum, up to infinity. The absolute value of 0.01, it is less than 1. So what that means is that we can write the repeating decimal as a fraction using the formula a over 1 minus r, where a is the first term and then r is the ratio. So we'll substitute a equals 0.85 and r equals 0.01 into a over 1 minus r, and we'll evaluate 2.858585858585 repeating. But we're not going to forget the 2 plus. We're just going to put in a, which is 0.85, over 1 minus 0.01. And this is going to turn into this. All right, and I can simplify this further. And this is going to equal 283 over 99, and that's going to be our answer. All right, let's do another one. For the following telescoping series, find a formula for the nth term of the sequence of partial sums, denoted S sub n. Then evaluate the limit as n approaches infinity of S sub n to obtain the value of the series or state that the series diverges. Now we're working with the infinite series that starts at 1, k equals 1 to infinity, of 1 over k plus 2 times k plus 3. Alright, now in order to find a formula for the nth term of the sequence of the partial sums, we have to first rewrite 1 over k plus 2 times k plus 3 using the method of partial fractions. So we're going to do some partial fraction decomposition. This stands for partial fraction decomposition. So we have 1 over k plus 2 times k plus 3. We're going to rewrite this. We've rewritten it as a over k plus 2 plus b over k plus 3. Now what we're going to do is multiply both sides of the equation by the common denominator, which is k plus 2 times k plus 3. So what's going to end up happening is these are going to cancel, all right? Then what we're going to do is we'll distribute both of these to b over k plus 3, and then this k plus 3, it's going to cancel with this k plus 3. So we're going to we're going to just apply um, k plus 2 multiplied to b, and then likewise with this other a over k plus 2, this k plus 2, these are going to cancel, and then it's only going to get the k plus 3 multiplied to the a. So I can simplify this, distributing a and b to these binomials here. And then we'll end up with 1 equals a times k plus 3 times a plus b times k times 2 times b. Now what this is it's a system of equations. It can be thought of one or two ways. It could be thought of as a matrix, or it can be thought of as a system of equations, and I'll show you both. Right here is our system of equations, and I can also write this as a 2 by 3 matrix. Upon solving our system of equations, or our 2 by 3 matrix, we'll find that a equals 1 and b equals -1. I'm going to plug in what we found for a and b respectively. Alright, so we have the series from k equaling 1 all the way up to some number, and it's the summation of 1 over k plus 2 minus 1 over k plus 3. Now I shall write out the partial sums. Okay, so now we have 1 over 3 minus 1 over 4 plus 1 over 4 minus 1 over 5 plus 1 over 5 minus 1 over 6 plus 1 over 6 minus 1 over 7, and then an ellipses to show that it's going to continue onwards all the way up to the addition of 1 over n plus 2 minus 1 over n plus 3. So in order to solve this telescoping series, we need to regroup and combine opposites, or telescope, in the interior terms. This will leave a simple expression for S sub n. So we want the partial sum, so we want S sub n. Now I'm going to grab that 1/3 and I'm going to pull it out. Then what I'll do is I'm going to add that to -1/4 plus 1/4. It's going to go together. Same sort of thing as before. -1/5 goes with the positive 1/5. And now the -1/6 goes with the positive 1/6. In this parenthetical statement here, we're going to have -1 over n plus 2 plus 1 over n plus 2. And then at the very end, we're going to have 1 over n plus 3. So what's going to end up happening is, and this is why it's called a telescope, it's kind of cool, but cancel, 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 cancel. And then what we'll be left with is just S sub n equaling 1 over 3 minus 1 over n plus 3. And then what we'll do is we'll obtain the values of the series, and we're gonna determine the limit of S sub n equaling 1 over 3 minus 1 over n plus 3 as n approaches infinity. We want the limit of S sub n as n approaches infinity. Now we determined S sub n to be 1 over 3 minus 1 over n plus 3. If we plug in numbers for n in this statement here, like let's not even focus on, let's just totally ignore the 1 over 3 at this point in time. We're just gonna ignore it for now because it's independent. It's not affected by n, right? If we start plugging in numbers for n as it approaches infinity, we're gonna be putting it in this n spot here. And if we think about like a number line, this is positive infinity. This is the direction of positive infinity, so we'll have 1, and then we'll have 2, and we'll have 3, 4, 5, and so on and so forth, right? And it's going to keep going forever. So as n approaches infinity, as n starts moving into the positive direction, what's going to start happening if we plug in numbers for n? So if we plug in 1 into 1 over n plus 3, we're going to have 1/4. 1 divided by 4, 0.25. Then we're going to plug in 2, right? So 1 divided by 5, because it's going to be 1/5. 2 plus 3 is 5. 1 over 5. It's going to give us 0.2. If we keep plugging in numbers, for example, like we're going to keep going in the positive direction. So if we start plugging it, let's say we plug in 12, we're going to have 12 plus 3, which is going to be 16. 1 divided by 16. Okay? Then let's say we want to plug in 20, right? It's going to be 1 over 23. And so then if we do 1 divided by 23, okay? And then let's say we want to plug in 100. 100, we're going to, because we're going to keep moving into the positive direction. So if we plug in 100 for n equals 100, we're going to have 1 over 100 plus 3, which is going to be 103. So it's going to be 1 divided by 103. These numbers, they're just getting smaller and smaller and smaller and smaller. These numbers are going to keep getting smaller and smaller and smaller. It's going to approach 0. So we just say that the limit as n approaches infinity for 1 over n plus 3 is going to be 0. So this here, it's going to go to 0. So 1/3 minus 0, well, that's just going to be 1/3. Therefore, the limit as n approaches infinity for s sub n is going to be 1/3. And that's our answer. This question says, for the following telescoping series, find a formula for the nth term of the sequence of partial sums denoted s sub n. Then evaluate the limit as n approaches infinity for s sub n to obtain the value of the series or state that the series diverges. In the series here, it's from k equaling 1 to infinity, and it's the summation of 4 over the square root of k plus 4 minus 4 over the square root of k plus 6. We're going to write the nth term in the enumeration of the partial sum. Enumeration means that you're writing out the first several terms of the partial sum of s sub n in order to be able to see what cancels in the telescoping series. So let me show you what that's going to look like. So here, this was k equals 1, and I plugged in 1 for k for each of these. Then I added that because this is a summation, and then here k equaled 2. All right, and then the ellipses, it means that you continue onward. But then the last 3 terms here for this one was k equals -3. And then for this one here, it was k equals -2. And then for this one here was k equals -1. And and we're going to use the telescoping series method to determine the sum. So first I'm going to write out more of the partial sums just to be clear. This is negative 4 over the square root of 7. So negative 4 over the square root of 7 is going to cancel with positive 4 over the square root of 7. And then negative 4 over the square root of 8, it's going to cancel with 4 over the square root of 8. 4 over the square root of 9, negative 4 over the square root of 9, well, it's going to cancel with positive. So what we'll do is we'll drop the parentheses. So in essence, everything in the middle disappears. It all cancels. The only things that are left are the first 2 positive terms and the last 2 negative terms. And then what we're going to do is rewrite the first 2 terms by rationalizing the expression. We can rationalize 4 over the square root of 5 by multiplying both the numerator and the denominator of this expression by the square root of 5, and that's going to give us 4 times the square root of 5 over 5. Alright, then we're going to do the same thing with 4 over the square root of 6. We have 4 times the square root of 6 in the numerator and then 6 in the denominator. Right, so s sub n becomes 4 times the square root of 5 over 5 plus 4 times the square root of 6 over 6 minus 4 over the square root of n plus 5 plus 4 over the square root of n plus 6. So now what we want to do is evaluate the limit of s sub n as n approaches infinity. The question is, what does the partial sum s of n get closer and closer to as n becomes very large? What's the limit? We see that this first binomial, it's just constant, right? It's not subject to change. It's not going to change when n changes. It's not affected by n. On the contrary, this binomial here, these guys are going to change. So we'll break it into 2 pieces. S of n equals constant minus what's dependent on n. Let's think about what happens as n approaches infinity. As n approaches infinity, we'll see that here, n plus 5, if we plug in 1, and then we plug in 2, and then we plug in 3, and then we plug in 4, don't even worry about the radicand right now. Don't worry about the radical. Just look at the n plus 5. Uh, set n to 1, 2, 3, 4, 5. It's gonna get huge. It's gonna grow and grow and grow. And then as for the n plus 6, it's the same thing. If you start plugging in numbers 1, 2, 3, 4 in a positive infinity direction, it's gonna start getting really large. And even with the radicand factored in, it's still, the terms are both going to get really, really, really huge. 1 over the square root of n plus 5, as you start plugging in numbers in the positive infinity direction, it's just going to go to 0 because the denominator is getting giant. It's getting catastrophically big. It's going to continue to get larger and larger in the positive infinity direction for both of these. And what happens when you divide a number by a larger and larger and larger and larger number? Well, it gets closer and closer and closer to 0. So by convention, both of these approach 0. So then we could just say that this whole parenthetical statement here is just going to go to 0. So we literally just have s of n equals 4 times the square root of 5 over 5 plus 4 times the square root of 6 over 6 minus 0. Alright, so this is just going to equal 4 times 5 over 5 plus 4 times 6 over 6, right? Because we're just subtracting 0 from that. So that's what we're going to have. So what that means is that the series converges. If we work through this, the answer is going to be approximately 3.421847544, and that's actually the value that the series converges to. So this is our answer. This is our answer or this, but we'll rock with this. This question says evaluate the series or state that it diverges, and it's the summation from 2 to infinity of 2 over 3 raised to the power of 3 times k. So the first thing that I'm going to do is rewrite the series. What I'll do is I'll distribute this 3 to both terms in the parentheses. 2 raised to the third power will be 8, and then 3 raised to the third power will be 27. So to do this, we first need to figure out what the value of a is. Now, remember, like before, a is going to be the first term in the series. So basically, what we'll have to do is we'll have to raise this to the first term in the series, which in this case it's k equals 2, so we'll have to raise it to the power of 2. So we have 8 over 27 raised to the power of 2. We got s sub 1. And we already know that s sub 1 is going to be equivalent to 8 over 27 raised to the second power. And then s sub 2 is going to equal 8 over 27 raised to the third power. And then r equals some term in the summation divided by the term that comes before that term in the summation. So that means we could find r as follows. So if you take 8 over 27 cubed and divide it by 8 over 27 squared, you're going to get 8 over 27, and therefore the ratio is 8 over 27. Now, since the absolute value of r is less than 1, the series converges, and its value can be given by a over 1 minus r. So the answer to this is going to be 64 over 513. However, I've also learned of this other way that you can solve this sort of equation here, a over 1 minus r. And it's a mathematical trick shot of sort. It's a mathematical trick shot for complex fractions. So let me show you guys how to do it. What we'll do is we're going to multiply 27 squared to both the numerator and the denominator. The reason that we're multiplying 27 squared is because it's going to get rid of the complex fraction. So we'll multiply the 27 squared to the 1, and then the 27 squared is going to cancel out, one of the 27 squares in the denominator, but there's still going to be a 27 square left because it's raised to the second degree. So we'll have 8 times 27 in the denominator. And then if you work this through, you're going to get 64 over 513 as well. And that will be our answer.